Okay, question 9 of the 2019 paper. Chlorine is used in the production of many other chemicals. Chlorine can be produced by the reaction of hydrogen chloride with air using the Decon process, and we have a nice little reaction pathway diagram, okay, and an equation. Using the potential energy diagram, determine the activation energy in kilojoules per mole for the forward reaction. Okay, so starting at 0, I need to get to the top of the curve here. I find this really difficult to read off on the screen, but I'm happy that it's 220 kilojoules, and you can put in the plus if you wish, but 220 kilojoules per mole. Right, part 2. Explain why increasing the temperature in the Decon process results in less chlorine being produced. Okay, so we have very clearly here a dynamic equilibrium with a forward reaction is exothermic. That's what you need to recognize. Okay, so if the forward reaction is exothermic, then what happens when we increase the temperature? So we increase temperature, then what I'm doing is favoring the endothermic. This is Le Chatelier kicking in, and this is you saying whatever you do to a system that is at equilibrium, it will move to minimize that disruption. So increasing the temperature is going to favor a reaction which removes that energy from the system. So it's going to try and do more of the endothermic. So it's favoring the endothermic, which is favoring the back reaction. So therefore you get less yield from the forward. Okay, B. One lab method for preparation of chlorine gas involves adding concentrated hydrochloric acid to potassium permanganate. The chlorine gas produced also contains small amounts of hydrogen chlorine gas. To remove the hydrogen chloride gas, the gases are bubbled through water, and then finally insoluble chlorine gas is collected. Okay, so I'm expecting you to do very carefully so you know that everything's connected and you're not trying to go through walls and things like that. Oh, this is a terrible, terrible diagram. Let me try and clean this up a bit. Okay, right, I think the simplest thing to do is to bubble through. We need a test tube, a rather big one compared to the size of the conical flask, but let's assume it's just closer. Okay, so we need some water in there, and then what we're going to do is bubble the gas into that water, okay, and then we're going to collect it above the water. In fact, to make this cleaner, I would prefer if I'd drawn it like that. Okay, right, and then so all I need is a stopper up here so that I can do my connections. This one is going to go off and connect to the other side. I'm really sorry, but I just can't draw neatly on these graphic pad things. And then this one needs to connect up to here again, as neatly as you can manage. Okay, what you need to do is to label that as water, because otherwise you're not showing what it's doing. Okay. Right, it then tells you it's insoluble chlorine gas. Now, that actually gives you two options for the collecting. I think the simplest collection is to just collect it in a very neatly drawn, and that's not as neatly as it should be because this should be closer. These bits here should be closer together. But the easiest, I think, is just to use a gas syringe. Because it tells you it's insoluble, then what you could do is do downward displacement of water. So put in a trough, put some kind of collection vessel, whether it's a measuring cylinder or a test tube or whatever you like, and then we want the collection, or the delivery tube rather, coming along here and into this, and then we need to clearly show that this is actually full of water, and then we are collecting our chlorine gas. And we would do the same here, either writing chlorine gas or writing the formula. Okay, oh, we'd need to label that as well, water. And I'd probably measure that, put that as measuring cylinder or test tube or something, so I was showing what that was. So 2 marks because you've got 2 parts to that. Right, got a Hesse's law question. Carbon tetrachloride, CCl4, is prepared by the reaction of chlorine gas with methane. Calculate the enthalpy change in kilojoules per mole for this reaction using the following information. Okay, so I'll run both forms. I'll use algebraic and then I'll do your full, fix, flip, all that kind of stuff. Right, so this is your not sure. Okay, this is my A, my B, and my C, or my 1, 2, 3, whatever you want to call it. Okay, right, let's see what each of them is doing. So this one The A is for my methane over here. B is for my carbon tetrachloride, and this one is for my hydrochloric. Okay, so pretty straightforward. Delta H is equal to, so A is on the wrong side, so I'm going to flip it. Okay, and then B is on the correct side, and actually it's fine. I've got nothing to do with that in terms of numbers. C is on the correct side, but I need to times that by 4, so 4 of delta HC. Okay, so that is going to be plus 75 minus 98 minus 368 minus 391 kilojoules per mole. Okay, so if you like it that way, grand. If you don't, here's the full kind of method. Right, so let's start with, we have our target equation and we have all of our data equations. First thing I need to do is to fix all of my data equations to my target. So this one is fine because it's a 1 and a 1. This one is fine because it's a 1 and 1. This one, however, is a 4 and a 1, so I'm going to have to multiply this by 4. So here's my 4. I change that to from a half to 2 and a half to 2. And I'm going to times this by 4. So this then becomes minus 386. Okay, get rid of that. Right, so I've fixed. Okay, because we've done target. We've checked we've got all our data. We've done fix. So our next thing is flip. Okay, so any of these equations which are in the wrong side, I now flip over. So the only one that's on the wrong side is my first one. So if I flip that over, it now becomes CH4 going to C plus H2O, H2O, 2H2, and then I also need to flip that to become plus 75, okay? And I'm now going to get rid of that, okay? So I've got my target, I've got my data, I've done a fix, I've done a flip. Now I could just add up at that point, but what I can also do is merge and cancel, just to be absolutely sure that I've got the same thing that I expected to have. So myself, and it always gets a little bit messier, but I do think it really does help a lot sometimes to use this. Okay, so I'm going to have CH4 from here. Okay, I'm going to have my carbon is actually on this side and on this side, so I'm going to just cancel that out. Not going to put that down at all. I've got 2 chlorines and another 2 chlorines here, so plus 4 Cl2, and I've got 2 hydrogens, but I've also got 2 hydrogens on the other side, so I can cancel those ones out. And then I've got CCl4, and I've also got 4 HCl. Now I check that against my target equation, and I'm absolutely certain I've got this right because I have the same equation. So all I need to do now is just add up my plus 75 that I've got here, my minus 98 which I've got here, and my minus 368 which I've got here, which is exactly the same thing that I did with the algebraic, but you've got kind of internal checking. And if this is the way you do it and this makes sense to you, please just do this one, okay? And it gives you exactly the same answer. Okay, that's the question.